on example 4, find the sum of each geometric series. All right, this is going to be so easy because we have conditions by which our geometric series converges, and we also know what the series is supposed to converge to, what the sum is, if it does in fact converge. Let me go back to it, right? So we basically first examine our common ratio, our R value, and we check to see, is it in between -1 and 1? If it is, then it converges. If it is outside of that area, that interval, then it's going to diverge. If it does converge, it's going to converge to the sum first term over 1 minus the common ratio. Okay, so let's take a look at the first one. We've got the sum, n equals 0 to infinity. Notice it does start at 0, which is nice, because if it doesn't start at 0, we got to do something else, of 3 over 2 to the n. All right, let me switch over here so I can actually write on the screen. Okay, so I want to first figure out what my R value is. Now I'm going to rewrite this just a little bit so it's a little bit more obvious what the parts are. This 3 that's on the top, it's just some constant number. I'm going to pull it out right front. Okay, and then what I have left over is 1 over 2 to the n. That's the same thing as the sum. I'm going to have the 3 on the outside, and I'm going to put in parentheses the whole entire 1/2 to the nth power, right? Because 1 to the nth power, it's never going to change. So the 2 that's down there on the bottom, it's really a 1/2 in disguise that we're taking powers of. I wanted to do that because that's what our R value is. R is equal to 1/2. Well, if R is equal to 1/2, then that means that this thing is going to converge. And on questions like this, if it appears on a free response question on the AP exam, you want to point it out. That you want to say that this thing converges since R is, or maybe even the absolute value of R, is less than 1. All right. Now I know that it converges. I want to figure out what does it converge to. So I need 2 pieces of information for that. I need the first term and I need the common ratio. Well, we already found the common ratio. The first term is supposed to be this 3 that's right there. So let's just say that I forgot that that's the first term. Or it doesn't start at 0. To get the first term, it's very, very easy. All I have to do is plug our 0 into our formula to get what the first term is. So I'd have 3 on top and 2 to the 0 on the bottom. 2 to the 0 is 1. I get a 3. There's our first term. So our A value is equal to 3. So our sum should be our first term, 3, over 1 minus the common ratio. And now I just simplify it. I get 3 over 1 minus 1/2 is 1/2, which is equal to 6. Basically multiply the top and the bottom by 2 to resolve that common ratio, complex fraction. Those are the words I'm looking for. Okay, so that means that the more and more terms I add to this geometric series, I'm getting closer and closer to the number 6. Oh, which reminds me, since we have a sum for this infinite geometric series right here, let's apply it to, take a little break, and apply it to the one that we did for Zeno's paradox, right, which is right up here. Let's get to the actual statement of it after I make you completely dizzy, which is right here. So notice that we already have an equation or a sum, and it does start at, this example starts at 1. That's not a big deal. My common ratio, if I rewrite this thing, n equals 1 to infinity. Common ratio, I'm going to rewrite it just like I rewrote the other one. It's basically 1/2 that we're raising to the n. And there's an implied, say, 1 that's right out in front of it. Okay, so I know since this R value, 1/2, R is equal to 1/2, which is less than 1, this thing absolutely converges. Not only does it converge, the sum of this should be equal to the first term divided by 1 minus the common ratio. Well, since this one does not start at 0, it's not necessarily the number that's right up in front. So our first term in this case, if this is the series that I'm going to work with, I need to plug 1 right in here for n, and I'd have 1/2 to the first power, which is a half. 1/2 is our first term. Divided by, and you can see also the half is the first term right there. Okay. Divided by 1 minus my common ratio, which we also explained was a half. All right, now just keep simplifying. I got 1/2 over 1 minus a half is a half. Half divided by half is in fact 1. There we go. So there's another way to go through that. But of course, we didn't know all of that stuff whenever we were first examining this particular example. All right, let's go back to example 4. So on example 4, we got another one on number 2. A geometric series. How do I know it's a geometric series? I know it's a geometric series because I've got some sort of number that I'm raising to a power, right? Maybe there's a number out front, like in this case it's understood 1 or whatever, or maybe there's not. Okay, so the common ratio is the thing that we're taking powers of. Our common ratio in this case is 3/2. I know that 3/2 is absolutely bigger than 1. So it's like I am getting closer and closer to these terms equaling 1.5, and I'm adding up an infinite number of 1.5s. What's going to happen to that series? This thing is going to diverge. Do not plug the numbers like the first term and the common ratio into the formula to get a sum, because this thing is supposed to shoot off to infinity. But if you were to try to plug these numbers into the formula, this is what you'd get. Sum is equal to the first term. If I plug 0 in here, I'd have 3/2 to the 0 power. You'd get 1 over 1 minus your common ratio, 3 over 2. That is 1 over 1. Let's see, that would be -1/2, right? -1/2, which is equal to -2. But really what this would be is -2 times, when I take the limit of the rest of this thing, going off to infinity. So this thing is totally misleading. You never ever get to use that formula unless you already know that our geometric series converges. And I know it converges when that common ratio is between positive and -1, but not including positive and -1. Okay. Let's go back to the slideshow here. We've got another example. Determine whether the series below converges or diverges. If it converges, find its sum. So this time I'm not given it in summation notation. I'm just given a list of numbers, a sequence of numbers with plus signs in between them. And we're just going to check to see, well, here's a hint. We've only done one kind of series. It's geometric. I wonder if it's geometric. That's one of the things that you want to try. Matter of fact, it should be one of the first things you want to try, because the geometric series, as you're going to see as we go through these lessons, it's the easiest. It's probably the reason why it's in this first lesson here on series. Okay, so I'm going to rewrite this first term as maybe 7 over 1 so that they're all fractions. And kind of like I did with the partial sums for the 1/2, the Zeno's paradox one, let's just see if there's a common ratio. Let's see if we're just multiplying by the same exact number each time. So what do I have to multiply 7 by to get 28? I think that's times 4. And then what about 28 and 112? Let's just see. Is 28 also times 4, 112? Let's see, that would be an 80 and a 32, which is 112. Oh, yeah, checks out. So that's times 4. Times 4, right? So that'd be 4, 4, and 8. Yes, definitely. So times 4. We're in good shape right now. Let's check the bottom. So obviously down here, 1 times 5 is going to give me a 5. 5 times 5 is going to give me a 25. 25 times 5. 125 times 5, and so on. So what's the common ratio? The common ratio is 4/5. If we were to divide any of these terms, like for example, if I were to take 28 over 5, over 5, and divide this by 7, maybe I'll write this like this, 28 over 5 divided by 7, maybe I write it like this, 28 over 5 times 1/7, then I can see, hey, these things cancel, leaving a 4 here is 4/5. If I do that to any term, any 2 consecutive terms, I'm always going to get 4/5. That's the common ratio, And look, that common ratio, its absolute value, okay, that looks like garbage. Looks like total garbage. The absolute value of that common ratio is less than 1, therefore this thing converges. That's my proof that this thing converges. And now we want to know, what does it converge to? What is the sum of that infinite series, that infinite geometric series? So my sum should be equal to the first term. I don't have a formula to get the first term, but you know what? Here it is. It's just 7. 7 over 1 minus my common ratio. My common ratio is 4/5. Simplify. I have 7 over 1/5 times the top and bottom by 5. You get 35. If I add up all of these numbers all the way, the whole entire thing, infinitely many of them, we're getting closer and closer to 35. Okay. Maybe 1 or 2 or 17 more. Example 6. Find the sum of this series. All right, so now looking at this one, we've got pluses and minuses, but it's set up to be very similar to the one that we just did before, where we don't have a formula for it. Instead, we just have this sequence of numbers. I don't know. All right, let's see. Let's go back over here. So I have some room to write. What the heck is this? I'm going to move this. Oh, that was secret answers you're not supposed to see. All right, I'll put the 5 over 1 like I did before, and let's see if we have a common ratio again. So it looks very obvious that I need to multiply maybe a 5 times a negative 2 here to get 10. And then that has to stay the same all the way across the top. So if I have a negative 10 times negative 2 also makes 20. Negative 2 times 20 makes a negative 40. All right, so it looks like negative 2 is on the top. All right, and then on the bottom, I don't want to keep using the negative sign because I already dealt with the negative sign up top. This is just times 3, and then 3 times 3 gives us a 9, of course. 9 times 3, 27, which implies that the common ratio is a negative 2 over 3. Again, I could have gotten that by just taking a negative 10/3, dividing it by 5, and simplifying all that down. You get a negative 2/3. But it has to work. You have to make sure it works for all of your terms, not just say for the first one. They could be trying to pull a fast one on you. Okay, so there's your common ratio. Is the absolute value of that common ratio less than 1? It absolutely is. That means that this thing converges. And we want to know, what the heck does it converge to? You don't have to worry about the fact that it's negative. Our formula is still going to work whether or not your common ratio is positive or negative. And our formula for this sum is the first term, which right there, I erased stuff, I didn't mean to, is 5. Over 1 minus our common ratio, so it's minus a negative 2/3, which of course means 1 plus 2/3. Which, if I keep going, let's see, that as 1 is 3/3, that's 5/3, which is 5 times 3/5. 5's cancel, and I get a sum of 3. I don't know why I'm like boxing stuff in green all of a sudden, but you know, whatevers. Let me come back to the slideshow for this because I got a couple of pictures for this. Remember that our common ratio is negative, and that we keep oscillating back and forth. We're alternating signs, positive, negative, positive, negative. So I've got a graph of what's going on here in a table of values. And this is the sum of those numbers. But notice that the sums are always a positive number. The sum is not a positive then a negative, a positive and a negative. That would be a bad thing. Here's a graph of it that helps us make sense of what's going on. If I were to draw some sort of line right here at 3, you can see that that's what it's getting closer to. It is oscillating. It absolutely is oscillating. And oscillation is not something that prevents necessarily from your limit from existing. It just has to oscillate close to a particular number. And this one's oscillating closer and closer to 3. Goes above, goes below, goes above, it goes below, but it's still getting closer and closer to 3, and therefore it converges. So if you take something like the sine graph, it's going from -1 to +1, but it's not getting closer, oscillating toward any particular number. And so by oscillation, that limit doesn't exist. This one, however, does. All right, I think we're going to do one more of these. Is the series below convergent or divergent? So this one looks a little strange. Sum n equals 1 to infinity of 2 to the 2n power and 3 times 3 to the 1 minus n power. So this is going to take a little bit of algebra to rearrange stuff so we can get it into a form that we can recognize. Again, the hint here is that I want to try to see if it's geometric, because if it's geometric, it's really easy to do. So that's what I'm going to do right over here. Now I'm going to do some algebraic manipulation here, and I'm going to rewrite, first of all, this first term as 2 squared to the nth power. This is basically using a power to a power algebraic rule for exponents. When you're raising a power to a power, you multiply the exponents, and so 2 to the second power, all of that to the nth power is the same thing as 2 to the 2n power. You multiply the two exponents, all right? And then I'm going to do the same thing over here on the second term, this one here, and by the same thing I mean something completely different. I'm going to rewrite that as 3 to the nth times 3 to the, 3 to the first power times 3 to the negative n power. Because when I'm multiplying with like bases, I'm going to add up those exponents, right? So I'm using that property of exponents too, right? And then I'm going to continue here to simplify. I really have 4 to the nth power, because 2 squared, of course, is 4, times our 3, but I'm going to take this 3 to the negative power, and I'm going to bring it down to the bottom as 3 to the nth, like that. So far, so good. All right, now I've got a little bit more to simplify here because I've got two things that are being raised to the nth power. So I'll rewrite that as 4 to the nth over 3 to the nth, and this is still times 3. Okay, and then I'm going to do that whole power to a power rule again for exponents and rewrite that as 4/3 to the nth power times 3. So our original summation simplifies down to this particular form, which we can then recognize as geometric, which is super handy because I just need to look at the common ratio here and determine whether or not the thing converges. My common ratio here is 4/3. And 4/3 is definitely bigger than 1. What does that mean? That means that no matter what, the sum of this is going to diverge. There you go. All right, that breaks up or ends this particular lesson. A whole bunch of examples using some geometric series. But there's going to be more. But this is a nice stopping place. And then we'll look at some geometric series kind of in disguise, as we'll see.